Hey everyone, this is Dr. Walker. In this video, we're going to go over examples from v529 properties of conductors in static equilibrium. Let's look at the first question. A point charge is located a distance r from the center of a neutral metal sphere, and we want to find the electric field at the center of the sphere. So feel free to pause the video and think about this. All right. So if you were trying to figure out how the Q here is going to produce an electric field over here when it's a distance r away, and we do have a radius r, well, then you're thinking too hard about it. The key here is that this is a metal sphere, and metals are conductors. And we just learned one of the properties of the conductors in electrostatic equilibrium is that the field inside a conductor is always going to be zero. And the choice was hidden. These got mixed, but this is supposed to be A, B, C, and then the choice D was 0. So hopefully you had that in your PowerPoint notes as one of the choices. I did fix it there. All right, so that was the answer. Field was 0 inside the conductor. Let's look at the next problem. We have a charge of plus 3 nanocoulombs in a hollow cavity inside a large chunk of metal that is electrically neutral. What is the total charge on the exterior surface of the metal? So on this surface here. So another property that we learned is that the charge is always on the surface of a conductor. So in this case, there are two surfaces, an inner surface and an outer surface. So if it's a neutral metal sphere conductor, then we know that the net charge must be 0, but since there's charge inside here, it's going to cause the charge to redistribute. We know the negative charges want to be near the positive, and the positives are going to want to be far away. So it turns out that there will be negative 3 nanocoulombs on the inner surface, and thus positive 3 nanocoulombs on the outer surface, because we know that these two added together must be 0. So the answer is plus 3 nanocoulombs. But how do we know that it distributes that way? Why couldn't it be negative 2 and 2, right? That would also equal 0. Well, we know that the electric field must be 0 inside the conductor. So if we construct a Gaussian surface inside this conductor, let's say right here, if we have a Gaussian surface here, we know that since the electric field is 0 through the surface, we know that the net charge enclosed must be 0 from Gauss's law. So that's how we know that the charge distributes this way. Let's look at a third example here. We are finding the field outside an infinite conducting plate of uniform surface charge density sigma. Now, we did a similar problem in Chapter 6 with Gauss's law, where we found the electric field outside a non-conducting infinite plate. But this is a conducting plate. So there is going to be a very slight difference. This is a Gauss's law problem. We just weren't ready to do it in Chapter 6 because we hadn't talked about the properties of our conductors yet. So that's why I'm bringing this here in this little example, but this is a very important result. So the flux is equal to the charge in over epsilon naught. And so when we did this for a non-conducting plate, we said that E dot dA was always 2EA because in that plate here that, let's say, was positive charge, and we had that Gaussian cylindrical surface, we had a field going through each area in opposite directions, and so we got flux through both surfaces when we did that. But in this case over here, when we construct our Gaussian surface, let's say it's a cylinder here, and we're trying to find a field right outside this conductor, well, the field over here is going to be 0 because we're inside the conductor. So now the total flux through our surface is not going to be 2EA. For the conductor, it's going to be EA. So that's the only difference between this example and the one for an infinite non-conducting plate. So we're going to get Q in, we can rewrite that as sigma times A, surface charge density times area. And then we can see that the areas cancel out. So we get the field, the magnitude of the field as sigma over epsilon naught, while for the non-conducting plate, it was sigma over 2 epsilon naught. Let's do one final example. In this example, I put it here. It's to explain another property of the conductors in equilibrium, which is that the surface charge density and the electric field is stronger when you have a sharper point. So I thought it would be very good to show this. So the way that we can show this property is by considering this kind of situation where we have two conducting spheres connected by a metal wire. So that means that we can just treat these two metal spheres as just one conductor, one big conductor, because they're all connected. And they're very far apart so that one sphere will not affect the charge distribution of the other. Find the ratio of the electric fields at the surfaces of the two spheres. So because this is just one big conductor, then the surface is all at the same potential. And we can call it KE Q1 over R1, or we can call it KE Q2 over R2, right? The potential here at this surface is going to have to be the same as the potential on this surface. So that's the first thing. And then the other thing is now we can take the ratio of the electric field. So let's do the ratio of E1 to E2. And we know that the fields are given by KE Q1 over R1 squared for the field here at the surface of the top one, and then KE Q2 over R2 squared for the bottom one. And then the trick here is to, oh, and this was supposed to be in R sub 2, not R squared here. The only difference between the field and the potential is a factor of 1 over R. We know that the field is 1 over R1 times V, right, for this one. And then over here, we can say, well, it's 1 over R2 multiplied by this potential, which is the same as this potential, which we can just call V. So the V's cancel out, and we get R2 over R1. So this is just a little exercise to show, okay, the field is going to be stronger when the surface has a smaller radius of curvature. So I thought that was a cool little proof to show, and that concludes this video, and it concludes Chapter 7 videos.